In this lecture, we're going to look at a function called the beta function. So the beta function is defined in this way. So the function is a function of two numbers, p and q, and it's the integral of 0 to 1 of x to the p minus 1, 1 minus x, q minus 1 dx, where p is a number greater than 0 and q is a number greater than 0. So if we have two positive numbers, p and q, then we can solve for this particular function. Now let's kind of play around with it a little bit. So let's say that x is equal to 1 minus y, which would mean that dx is equal to minus dy. So I'm going to do this kind of variable substitution, and beta pq is therefore equal to 1 to 0, so I had to change the limits, 1 minus y, p minus 1, y, q minus 1, minus dy. Now I can take that minus sign up front, so I can take it out front. Okay, so now my integral is minus 1 to 0, the quantity 1 minus y to the power p minus 1, y q minus 1 dy, and so that minus sign is going to flip the limits on the integral, so I would get the integral of 0 to 1 y q minus 1, 1 minus y, p minus 1 dy. So looking at that, that just looks like the beta function again, except for we've swapped the role of p and we swapped the role of q. And so since x and y again are just dummy variables, they don't really have any meaning yet, then I could write the beta function with an x, I can write the beta function with a y, and so in the end, what we have is that the beta function for pq is equal to the beta function if I switch them and make it qp. So, if p was 1 and q was 2, then the beta function of, b12 would be equal to the beta function of 2 comma 1. So let's take a look at this a little further and say, let's consider my variable x is really the variable y divided by a constant a. Okay, so let me put that into my formula. 0 to a now of y over a, p minus 1, 1 minus y over a, q minus 1, dy divided by a. So all I did was do a variable substitution. So I can take the 1 over a out front. I can actually take a 1 over a p to the minus 1 out front. I can take a 1 over a q minus 1 out front. And what I'm left with now is the integral 0 to a, y, p minus 1, a minus y, q minus 1, dy. And so if I rearrange this a little bit, I would get 1 over A P plus Q minus 1. And then the integral of 0 to A, y, P minus 1, A minus y, Q minus 1, dy. Now we have a beta function that can range not from 0 to 1, but from 0 to any number A. So now we have a beta function in the range of, basically 0 to A. So I can set now an arbitrary limit, not just, as long as A is a positive number, I can make it any range. So let's take a look at another example, and that is, let's say x equal to sine squared theta. So that's kind of interesting. So if I look at dx is equal to 2 sine theta cosine theta d theta, and 1 minus x is 1 minus sine squared theta, which is just cosine squared theta. So now what I'm going to do is I'm going to put that into my equation for the beta function. So the limits now would be 0 to pi over 2, because that's when sine squared of theta is equal to 1. So it's 0 to pi over 2. So this would be sine squared theta p minus 1 cosine squared theta q minus 1 2 sine theta cosine theta d theta. So okay, so let's try and work this out a little bit more. So that's 2, the integral, 0 to pi over 2. I could actually make this into a sine 2p minus 2 cosine 2q minus 2, and then I'd have sine theta cosine theta d theta. Okay, so you may see where I'm going with this. I can now bring the sine theta and the cosine theta into it and adjust those exponents. So I'd have 2, 0 to pi over 2 sine theta, sorry I forgot the thetas, of 2p minus 1 cosine theta 2q minus 1 d theta. So now that integral is a little bit smaller than it was before, and it looks a little bit more compact. So now I can basically write it not in terms of x's, but maybe I want to write it in terms of theta. So we worked out the beta function for a range of 0 to 1. We worked out the beta function for a range of 0 to a. Now we've worked out the beta function in terms of an angle theta. So let's try one more. And let's take a look at what if x was equal to y over 1 plus y. So in that case, dx would be equal to 1 over 1 plus y plus minus y over 1 plus y quantity squared dy, and that, if I put it under the same denominator of 1 over y, of parentheses 1 plus y quantity squared, then I would have 1 plus y minus y dy, or 1 over 1 plus y quantity squared dy. Okay, so what does that give us? Well, first let me change the limits. So when x is equal to 0, y is equal to 0. When x is equal to 1, y is equal to infinity. So now I can rewrite the beta function in the range of 0 to infinity, y over 1 plus y, p minus 1, 1 minus y over 1 plus y, q minus 1, dy over 1 plus y quantity squared. Okay, so how can we rearrange that a little bit? Well, I can make this y p minus 1 over 1 plus y p minus 1. I could group together this. So this would be 1 plus y minus y over 1 plus y, q minus 1, dy 1 plus y quantity squared. So that gives me y to the p minus 1 over 1 plus y. Well, let's bring over the 1 plus y squared. So that would be p plus 1. And then this would be 1 over 1 plus y q minus 1 dy. And so if I now combine those, I would get y p minus 1 over 1 plus y of p plus q, and then the 1 and the minus 1 cancel, dy. So now, if I want to write this over the limits of 0 to infinity, I can rewrite the beta function as 0 to infinity, y p minus 1 over 1 plus y p plus q dy. And again, since y is just a variable, I haven't given it any meaning yet. It's just a dummy variable like x or t or anything. So in the end, we now have a number of ways that we can write the beta function based on their range, whether it's 0 to 1, 0 to a, 0 to infinity, or 0 to pi over 2.